Swayam Prabha. Digital India. Educated India.
Alright guys, so in the previous videos you had seen what is a directed graph, how can you work using NetworkX packages in Python, and how can you deal with directed graphs in NetworkX. Also we had seen what is points distribution method, what is the procedure in which you play and how would you distribute the points, how would you share your points with your neighbors. Also we had seen a simulation in Excel spreadsheet that if you keep repeating for multiple iterations, the values converge. That is, the difference between this iteration and the previous iteration is either insignificant or there is no difference at all. So that difference is highly negligible. In that case, we say the values converge. So we'll now see a simulation using Python. So we'll get started. The first step, what you have to do is you need to create a directed graph. Okay, so let's do that. So how would you create a directed graph? For that we need NetworkX package. So let us import that first. Import NetworkX as NX. So we have imported it. So let us now go ahead with creating the directed graph. So how would we do that? G is the graph object is equal to NX dot digraph. This is how you create a directed graph. So we have created it. This is an empty directed graph. So the next step is you should add the nodes. So let us do it. G dot add nodes from. Yes. So we'll have to pass the list. So let us say we need some 10 nodes. We had taken a very small example of 3-node graph in our demonstration. Now let us take a slightly bigger graph, 10-node graph. Maybe you can simulate with 100-node, 1000-node graph. You can just keep extending the same thing to larger number of nodes with a complex graph. You can keep doing that. So let me now give a demo with a 10-node graph. So I am going to insert 10 nodes from 0, 1, 2, 3 up till 9. So using a for loop, a single line way, as we have seen in the prerequisites portion of this lecture series, we'll be doing that. So it is nothing but you just say I for I in range. How many number of nodes you wanted? You just need to give. I'm going to do it with a 10-node graph. So let me do it. 10. So the 10 nodes from 0 till 9 had been added to the graph. So the nodes are created. So now we need to add some edges. So let me say add edges. So I need to add edges and get back a new graph with edges. That is, currently we just have nodes and no edges. So I need to add edges and get that new structure as my graph G. So let me say G will be my new graph. I'll have to add edges. So that's what I have to do. I have created a graph object. I have added the nodes. Now I have to add the edges. So undefined name add edges it says. So that means I have used this name, but I have to define what this actually is. So let me go ahead and do that. Let me say define add edges. Okay, so first to add edges, what do you need? Nodes. Between two nodes there will be an edge, right? So we need to get the list of nodes. We need to access the nodes frequently, so we'll take the list of nodes. So let me say nodes is equal to list of G dot nodes. So we got the list of nodes. So now I need to pick a source node. Let me say S for source, for S from nodes, and I need to pick a target node. Let me say T for target from nodes list. I have picked it. Also I should see the source and target must be two different nodes. If it is the same node, it will be a self loop. It's like telling I like myself. everyone likes themselves. So capturing this information is actually waste of space or something like that. So we'll not do that generally. That's what we call as loop in graph theoretical terms. So we don't prefer loops generally. That's what we call as a simple graph. So we are going to construct a simple graph where there is no loops. So we need to see that these two are different nodes. So I'm going to perform a check here. If S is not equal to T, only then I'll think if I have to add an edge or not. So if I just like that keep adding an edge, what happens? This loop will run for all possible pairs, and what you get is a complete graph. I don't want a complete graph. I want a graph to be randomly generated. So for randomly generating, I have to again go ahead with this package random. So let me import it. Import random. So I have imported it. So I am going to randomly add an edge. So how could I randomly add an edge? So I can simulate it with a coin toss. So I may say that I just pick two different nodes. If they are different nodes, what I will do? So I have picked a node S, I have picked a node T, source and target. So S and T, I have picked two nodes. If they are two different nodes, what I have to do? I'll toss a coin. If I get a head, I'll put an edge. Otherwise, I won't put an edge. So if you toss a coin, what is the probability? What is the chance that you get a head? 1 by 2, right? Because head or tail, two possibilities. One of that possibility is head, which is your desired thing. So 1 by 2, which is 0.5 is the probability of your head. So I'm going to simulate that coin toss. If I get a head, I'll put an edge. Otherwise, I won't put an edge. So let me say, so I'm going to toss a coin. That is nothing but I'm going to generate a random number. That's what I'm going to simulate. So let me say R be my random number. I'm going to generate random dot random. What does this do? It will generate a random number in the range 0 and 1. So let me take 0.5. That is a probability for my head, right? So I'll say if this random number R is within 0.5, I consider that I have got a head. Otherwise, I'll say I have got a tail. This is how I'm going to simulate the coin toss process. So if this R is within 0.5, less than or equal to 0.5, what do? I consider it as a head. So if there is a head, I have to add an edge, right? So I will add an edge. G dot add an edge from source to target. So I have added an edge. So I'll do this for all possible pair of nodes, and whatever is the resulting graph, I'm returning the resulting graph. I'll return the graph G after adding the edges based on coin tosses. So coin toss is a random process. If you toss a coin, you get a head or you get a tail. So based on that, if you draw an edge, you will get a random graph every time. So you can experiment what happens. Instead of having a fixed structure, you get a different structure every time, and you experiment what happens with whether there is convergence with any structure. You can experiment it, and there will be convergence. You need to run for sufficient iterations, maybe 10 node graph. So I suppose maximum some 10,000 iterations, definitely there will be convergence. So why do I say this concretely? Because there are some mathematical results which say that there will be convergence in any structure. So just an intuition that I could give you is, just a hint is same, probability is a hint. You can delve deep into it if you are interested. There are mathematical results, there are proofs which state that definitely there will be convergence if you keep repeating this procedure. So you can simulate it. Say for example, I had taken as 100, 100, 100 each, right? Initially all nodes were having 100 points. That is how I had taken. So I can, instead of giving 100 points, if there are some k people, I can give 1 by k each. The sum turns out to be 1. So this is one thing in probability, right? The individual probabilities may be anything, but the sum of all the probabilities will sum up to 1, right? So you can consider it like that, and you can think of it as a probabilistic model, and you can prove that. It's slightly rigorous, the mathematical part, but it's not very difficult actually. You can understand it. All that you need to know is some amount of probability. If you are good with probability, you can look up to what the mathematical proof is, and you will get to know that definitely whatever be the graph structure, whatever be the initial configuration, initially we are starting with equal. Even if you start with unequal configuration, it will converge. Probably the number of iterations it takes to converge may differ, but it will definitely converge. So that is a mathematical result. You can experimentally verify this with different random graphs. You run it once, you will get a graph. You can verify whether there is convergence. Similarly, you can run it again. You can run it and you will get different graph every time. You can verify whether there is convergence. As per that mathematical result, there should be convergence. Let us see if it happens. Okay. So we have added the edges. So we have added the nodes. We have added the edges. Now what should you do? We should visualize the graph. Visualize the graph. So to plot the graph and visualize it, what do I need? I need this package matplotlib. So let me import it. Import matplotlib.pyplot as plt, a shorter form. So let me say matplotlib.pyplot I have imported. So what should I do? I should first draw the network. So I'll say nx.draw of the graph G, and I need to have a labels. Labels are nothing but the entries of the node. That is, this is node 1, this is node 2, this is node 5, so on. I need the labels. So I'll say with labels equal to true. I'll say this. So you will get the graph drawn with the labels, and now I have to show the drawn graph. I'll say plt.show. Okay, so done. So what we have done till now, we have created a directed graph. We have added a few nodes, added some edges. We have added edges randomly, simulating a coin toss, and we are going to visualize that graph. That's what we have done till now. Okay, let's go ahead, run this and see what happens. Let me run it. See, some graph got generated. Some network is there. If I run one more time, I get another network. Another time, I get another network. Some other network. So every time you are getting a random network. So on this, you can run your points distribution method and you can check whether there is convergence. As I have said, there is a mathematical result which says there will be convergence irrespective of whatever is your initial distribution, however you distribute the points, and as well as whatever is the structure of your graph, irrespective of that, you will have convergence. There is a mathematical result. Let us verify that in the upcoming parts of the video. That's why we are generating a random graph. So if you run this iteration, you will have a different output. Some other iteration, you may have a different output. So we are basically experimenting it for different structures. How is the behavior? We are basically experimenting. That's what we'll be going to do. So we'll do this in the upcoming parts of the lecture. Alright guys, so in the previous videos we had seen what is a directed graph, how can we work using network X, and what is points distribution method. We had simulated that in an Excel sheet with a small network, with a small graph with just 3 nodes we had simulated. Now we are proceeding towards checking what happens in a complex network having lot of nodes and edges. So as a first step, we had created a directed graph. We had added a few nodes and edges were added randomly, simulating a coin toss. Now we had visualized the graph as well. This is what we had done till now. Now we'll get started with the actual points distribution procedure. So let me get started. The first step is you have to assign initial points, right? Initial points. That is the first step that you have to do. Let's do it. So let me say assign points. Let me call, and so once I assign the points, I need to have a list of points, right? So this node 0 has got these many points, node 1 has got these many points, and so on. I need a list of points. So let me call that as points. So I'll assign points. So to assign points, I need to assign it for each node, right? So I need the graph. So from the graph, I'll pick each node and I'll assign points to the nodes. So I need this, and as you could see the warning, undefined name. So we need to define this. So let us define it here. Define assign points, and we use the graph G. So I have to assign the points. So first, as I have said, for each node we need to assign it. So let me first get the list of nodes. Nothing but list of G dot nodes. So let me get the list of nodes, and now I have to assign it. Assign the points. So I need a array points. Let me say P. I need a list. So for each in nodes. So for each node, I have to append how many points? We had started with 100 initially, right? So let us do that same. We have to append 100, and once all nodes had been assigned the points, you return this array P. So we had assigned the points. So what have we done? We take the graph G and assign points to each node, and we get back the points. So we take the graph G, we take the list of all nodes. For each node, we are assigning 100 points initially. That's what I'm doing. I'm assigning 100 points. 100 points I'm assigning initially. This is not hard and fast rule that you have to assign 100 only. You can experiment with different initial values. This is a seed value, as we can say. You can experiment with different seed values as well. As I have said, you can model it as a probability. You can say 1 by number of nodes. You initialize it and you can see what happens. You can try different things. So in this demonstration, let us take 100 as the seed value. We have 100 nodes. So we can have different seed values. With different seed values, the final convergence values would be different. But one thing would be the same. For example, we had taken in our 3-node demonstration that we had done with our Excel sheet, we had taken 100, 100, 100 each for each node. So 300. At the end, in convergence state, it was 120, 60, 120, that I remember. So it may be something like this. Instead of having 100 initially, if I had taken 10, the values may be different. If I had taken 25, the values may be different. But one thing that is same is, if you take the fraction 120 divided by the total 300 and 60 divided by 300, 120 divided by 300, that is 0.4, 0.2, 0.8. This is same. Something like that. Even if you take 25, 25, 25, at the end, if you take it, the individual point divided by 75, the total, you will get the same thing, 0.4, 0.2, 0.4. That distribution is maintained. So that is why I had given a hint. You can model it as a probability problem. See, the final sum is 1. If you model it, you are getting the distribution is constant. So you can model it as a probability problem, and you can mathematically, you can go rigorously and prove that definitely there will be convergence irrespective of whatever be the structure of the graph or whatever be the initial state you start with. And it's also not necessary that you have to start with equal points, equally 100 each. That's even not necessary. You can even start with 10 points for one node, 500 points for another node, 300 points for some other node. You can start with any configuration. At the end, you'll reach the stable state. The stable state there was 120, 60, 120, given that we started with 100 and 100. Or in terms of scale down to one version, it is 0.4, 0.2, 0.4. That was the stability state. Something like that. Every graph has got a stability state. That is a mathematical result. So, okay, let us come back. So we have assigned the points, and now the next step is you should keep distributing. Keep distributing the points. So if you keep distributing the points, you would get some final points. Let me call it as final points, the converged points, you can call it as the converged points you will be getting. You will get the final points by keep on distributing the points along the nodes of graph G. So, okay, again I got a warning, undefined name. So I need to define it. So let me copy and define it here. Let me define it. Define this and let me say. So I have to distribute the points among the nodes. So for that I again need the list of nodes. Let me say nodes is nothing but list of G dot nodes. I need to get the list of nodes. I've got it. Now I have to. Okay, so we have started with our definition of keep distributing functionality. So I have to start keep on distributing. As I say, keep distributing. So it is an infinite loop. So let me start in an infinite loop. So if it is an infinite loop, when will we stop? It's our wish, right? So Excel, even when we simulated, if I wanted, I can even drag it till 1 lakh iterations. You can drag it as you wish. So I'm going to give the control to the user. When he decides to stop, that will be the time he will stop. So I'm going to give the control. So till then it will be an infinite loop. So what should I do? I'll have to distribute the points to the nodes of the graph from this initial points configuration. Initially we have equal points. That's the configuration we are starting with, and we have to take that configuration and distribute as per our rule. Okay. So if you distribute the points, you will get a new set of points in the next iteration. So let me call that as new points. That will be my new points. So once I get my new points, I need to print my new points. What are my new points? I have printed. So once this new points have been obtained, you have to take this as your initial configuration and repeat the procedure, next procedure. So how would I do that? I have to say my points will be nothing but my new points. So basically what do you do? You get some initial configuration, you distribute it as per your procedure. After distribution you get some new configuration, the new points. So take that as your base configuration and repeat it. So in iteration 2, you took iteration 1 values as your base values. In iteration 3, you will take iteration 2 values as your base value. Right? So that's what we are going to do. That's why we are doing this assignment. And now you have to decide whether to stop or not. So let me say stop. I'll say is nothing but I'm going to get an input from the user. Let me say I'll take some key from the keyboard. Press hash to stop or any other key to continue. You can have any key. I have just taken hash randomly. You can have star, asterisk symbols, percentage symbol. You can have anything. You can have anything. That's not hard and fast thing. You can have anything. So I say you have to press hash. As long as the user presses hash, you have to continue. If you want to continue, you have to press some other key. If you want to stop, you press hash. That is the rule I am defining for the user. So I will get the input. Now given that user has given the input, I need to process it. If this stop value is equal to hash, then what should I do? I should break. I should come out of the loop. Alright, so once I have broken, so the user wanted to stop. Whatever is the value of new points, that will be my final points. So I need to return it. So I'll return new points. Right. Once I come out of the loop, whatever is the value of new points, I'll return it back. So I keep distributing. So what have we done here? we have assigned equal points initially, not necessarily that it has to be equal. We have done equal. You can try a different variant as well. As I have said, you assign randomly some values, then you see, you can use a random generator again. For example, from 1 to 500, you pick a random value and assign that as a point to the node. You can try different thing. We have started with the equal configuration, and after that, after you have assigned, you keep distributing the points. So in keep distributing, what are we doing? We have to distribute the points, and as a result of this distribution, you will get a new configuration. You print that configuration and take that configuration as your base and repeat that. You repeat that as long as the user doesn't want to stop. So as long as the user wants, keep repeating. If he wants to stop, he'll stop. In that place, you return whatever is the new points, whatever is the last configuration you have got. So you return that. Right. So here we have undefined name distribute points. Yes, we have to define it. We say distribute points. What is the procedure to distribute? We'll have to define it. We'll do it in the next part. Alright guys, so in the previous videos we had seen what is a directed graph, how can we work in network X, and then we had seen what is points distribution method. We had simulated it on a small network with just 3 nodes in Excel sheet. Now we had started with the programming part. We had created a network, we had visualized it. We are creating a random network simulating coin tosses. We had visualized that network. Then we had initialized the points equally, some seed value we had initialized. All the nodes are getting the equal points first at the first stage. Then we have to keep distributing. Under keep distributing, we need to now define how to distribute the points actually. So we'll do that now. So let me define it. Define distribute points on a given graph and a given points configuration. So let me distribute. So as and always, we need the list of nodes to operate. So let me get the list of nodes. List of g dot nodes. Right. So before starting, initially every node has given something to its neighbors. So it will have nothing. So let me say new points are initially 0. Right. So I need to assign it. So let me say for I in range length of nodes, that is how many number of nodes are present, length of nodes NODES. Okay. So for that we need a list as well, right? So let me say new points. Let me create a list. New points. Let me say new points. New points. Append 0. Why 0? Because the node has given everything to its neighbors and it has nothing. That is the state. Then we will come. That's how we had even introduced in the slides, right? So the node will give it to its neighbors. That's it. The next stage we consider what is it getting from. So if everyone is giving, someone has to get. So what is that it's getting is the next consideration. So first the giving part. This is the giving part. So we have to keep appending the 0 value because it has given everything, it has nothing. So this is your new points. So now let us say for n for node, let me say n in nodes. I take a node n, I'll say out for out edges. So we have to see the out edges and we have to share it with the outward edges, right? So I'm taking the list of out edges. List of g dot out edges, and you need to give the node ID. It is n basically. So I gave it. So how will this appear? List of tuples. An edge is represented by a tuple. Source, comma, target, something like that. List of tuples we will get. So if this is an empty list, what happens? So it need not share anything with anyone. It will just keep getting whatever it was having previously. So we'll handle that case here. If length of this list out is equal to 0, meaning that it has no outgoing edges, then it will just keep getting the same points what it had got in the previous iteration, right? So I should say the new points for this particular node n is nothing but new points of that node n previously plus whatever is the point it had in the previous iteration, the previous value of points. Whatever was the initial configuration will again retain. So it had got some, for example, say it had got some 10 points. Again it will get some 10 points. It need not share with anyone given that there is no outgoing edges. If there are outgoing edges, you need to share. If there are no outgoing edges, it will again get some 10 points. In next iteration, again some 10 points. It keeps accumulating. So that accumulation thing we have handled here, right? Okay. So if this is not the case, it is having some outgoing edges, then it has to share some points. So let me say share. It has to share. How should it share? It has to share equally among all its neighbors. How many neighbors are present? That is given by length of this list out. So how many outgoing edges? It has to share it equally. So whatever is the points it has been having, you have to divide it equally among all the outgoing edges. So that is the procedure. So we have got the value of share. And so this is the value of share. This much it has to give. To whom all it has to give? It has to give to the target nodes in the outgoing edges list. Right? So that we will see. So for the items in this outgoing list, what is the format of the items in the outgoing list? Source, comma, target. Right? So this is of the format source, comma, target. That is how the items in the outgoing list are. For each of this in outgoing list, your source will be obviously the same node n, right? Target differs. So we'll take the target value and we'll work on it. So the new points of target is nothing but whatever it had earlier plus what is the share it is receiving from this node n. So why we are having this new points plus share? Why do we have this? Because whatever, for example, we had one node where it will get half from, I guess it's node C, half from node A and fully from node B. So it had different shares. So when you run the loop with node A, you would have given some half. When you again run it with node B, what happens is, if you just say it is equal to share, the previous share, whatever it has got from node A, that value will get destroyed. We need to retain that as well as this. That is why we are adding it. Okay. So this is how the new points are calculated. So, okay. Once everything is done, what you do? You return your new points. Right. So this is how the distribution occurs. Just let us see once this part. So we get the list of nodes, we have new points. Initially it is 0 given that they have all given whatever they have and they have nothing. So now given that they have given, someone has to be there to get. So each node will get some share as well. So we are going to see the getting part now. What happens? We are taking a node n and then we are seeing the outgoing edges. So to outgoing edges only it would have shared. So the outgoing edges, the target nodes, will get the share, will get the new points. So if there is no outgoing edge, what happens is this node will keep accumulating the same points in this iteration as well. So that is why I am adding the same points again. No, if that is not the case, there are some outgoing edges, then it has to share it. So it will equally share the points it has with all the neighbors. So this share has to be given to the neighbors. So it is of the form source and target. That is how you get the list of edges. So to all the target nodes, you have to increase this share. You have to give this share to the target nodes. That is what we are doing. The target nodes will get the value of share along with whatever it has got. And why we are doing this addition? Because a node may get different share from different nodes. To account that, we are doing this addition. So once you have computed it for all the nodes, you can return the list of new points. So that is how a single time distribution occurs. So this is distributing just for one iteration. So in this keep distributing function, you are repeatedly calling this distribute functionality and you keep repeating the process again and again till the user stops. Alright, I hope you are now clear with the procedure. Maybe you can take a pause, you can think what we have done in the previous parts, what we have simulated in the Excel sheet, what is the procedure we have explained. You think, you give a pause, you will understand it really well. So okay, let me clear the screen here and actually maybe I'll do it fresh. Okay, so the screen is clear here. So let me run it. Let me run. So I have got some values. Initially it was 100. Now I have got something 135, 103, 98, something I have got it. So it's asking me if I have to stop or I have to continue. I want to continue, so let me press some other key. I press enter key. It has continued. Continue, 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 continue. I keep continuing. After some time, see, did you see here? The values here as well as here, there is no much difference. I guess it has almost converged. So there is convergence. So I can stop here. Let's press hash. Yeah, it has stopped. So as you could see, we had some random graph structure. You can see some random graph structure is here. So I had done distribution once and this is the result of distribution once and it's asking me if I want to continue or stop. I had continued for a lot of iterations and at the end I found there is convergence, right? See the values here 136.8985, 136.8985. There is no much difference, so it has started converging. So once it converges, after that whatever be the number of times you repeat it, the same values will remain. So given that I had hit the convergence, I stop. That's what I have done now. So this is how we had checked the values of points after repeatedly distributing it. Now we have to rank the nodes based on the points it has accumulated. So for example, 45 is the minimal value. So this node gets the least rank. And 136 is the highest value. So this node gets the highest rank. Something like that. So I have to rank the nodes. So basically you can consider this as marks. So initially I am giving 100 marks to people and they are playing a game and distributing it. And at the end, whoever has got maximum marks, whoever has got minimum marks, I have to sort the nodes. I have to compare the result with the actual page rank procedure that is implemented in NetworkX. I have to compare that result. And so that we'll be doing in the next part of the video. Alright guys, so in the previous videos, we had seen what is a directed graph, how can we work with NetworkX and directed graphs, and what is points distribution methods, and how do we had simulated it with Excel sheet, and that was for a very small network, and now we had started off with the programming part with a complex network having a lot of nodes and edges. We had created a random network, we had visualized it, we had initially given equal points to all the nodes, and we had started the game. We had asked the nodes to distribute the points based on their outgoing edges, based on the structure they keep distributing, and we decide when to stop this game. That's just because in Excel we have the flexibility. We can extend that, we can drag the calculations to as long as we want. So something like that, same like that, I want to give the control to the user. That's why I had done it something like that, but the user will decide when to stop. So whenever the user stops, it will just say this is the final values. So something like that, we had got it right. So now what should we do? Once we get the final values, we should rank the nodes based on those values. And the next step would be to compare it with the actual page rank values that is provided by the built-in functionality in network X. So we'll do that. Okay, so after we are done distributing, we got the final points. So I have to, what should I do? Rank by points. Right, I have to rank the nodes by points. So let me say rank by points. Let me call it. So to rank the nodes by points, what do I need? I want the final points. So I want this. So I have to rank the nodes by points. Okay, so as you could see, it's undefined name. There's a warning message that's given. So let us define it. Let us define it. Okay, define this thing, and let me see how shall we start with it. So we have defined this functionality rank by points. So the first thing is, if you just like that, we have points is nothing but a list, right? So if we sort the list, it's simple and you just rank it. That's what you're saying. But if you sort the list, you will lose the information as to this point belongs to which node. So here we need to keep track of two information. Which node has got how many points. It's not just about how many points, it's about which node has got how many points. So we have to convert this list structure into a dictionary structure. We have to convert the list structure into a dictionary structure, and this dictionary structure will be applying the sort functionality that is defined on dictionaries, and this will be using to display the rank of the nodes based on the points they have accumulated. Alright, so as I said, I need a dictionary, so let me say D. Let's say dictionary D. So I have to have the node, the points are actually arranged in the same order. No, node 0 point is the 0th element of this list, node 1's point is the first element of the list, something like that. That's how it has been arranged. So it's just enough if I loop once. So I'll loop over for I in range length of points. So whatever is the index, that is the node ID as well in our case. Length of final points, basically this is final points, or maybe we can even call this as points as well. So there it was final points, and even here you can call it as points. So for I in range length of points, that is, I am going to iterate over the list. I am going to convert it into a dictionary with key I. The list index is what I am going to make it as a key. So that is same as node ID, right? So I am going to make it as a key. It's nothing but the corresponding value of points at that index. So I have created the dictionary. So now I should sort this dictionary. To sort the dictionary, we have a built-in functionality, sorted. You need to pass the items of the dictionary, and here dictionary has two things, key and value. We need to sort it based on the value part, right? So for that, you need to say key equal to lambda. So key here is nothing but based on what value you need to do. What is the factor based on which you need to sort. That is what you call as key, and lambda is a built-in functionality in Python. Basically it's like, for example, alphabetical order, at ascending order, at attendance order, or whatever you can call it as. How would you do it? Based on the first letter you will sort the names. A comes at the beginning, then comes B, then comes C, and so on. What if you have a different demand? You want to sort it based on the last letter. So in that case, you have to make use of a custom function that you are actually going to write, and based on that function you have to sort for your requirement. Something like that. If you have some other factor that you are defining, and based on that factor you want the sorting to happen, you will use this kind of a syntax. And lambda, because I'm not going to define a new requirement that is not present in Python. This sort by value is a common requirement, so Python has defined it. So it will say the factor f, let me call it f, is nothing but by f at the index 1. So key is at index 0 and value is at index 1. So this lambda functionality sort of converts it into a tuple format, and it will take the value at index 1 and it will sort based on it. So this is a defined functionality that has been defined in Python itself. In case you want it as a new requirement, here you can say key equal to my function, and based on that function it will sort. So what is the factor I should consider for sorting? That is what is denoted by this key. Okay. So my factor is nothing but I want it to be based on the first index value, that is based on the value of points I want the sorting to take place. The relationship between the node ID and the points is also preserved and sorting also occurs. So this is a specialty. So if once it is sorted, it will return a tuple, a list of tuples basically. So I need to print it. So I'll print this value. So given that I have sorted and printed, so the ranking part is done. So what should I do now? So once I have ranked, let me compare it with the default networkx function. I'm going to use that and I'm going to compare the results. So the default function of networkx is nx.pagerank, and you have to pass the graph. And it will return a dictionary basically. So that's why we had also used a dictionary, right? We had why dictionary? Because you need to you have to actually preserve the fact that this node has this many points. You have to preserve that fact. So let us say this is the result of your page rank, resultant dictionary nx dot page rank of G. Just you need to give the value of page rank, and these things, maximum number of iterations, how many iterations you want, you can customize it. You can do it as per your demands. But even if you don't give, there are some default values, it will be taken and it would be calculated. So we got the resultant, that's a dictionary, and same like this I need to sort and print the sorted values, right? So let me just copy paste this line. Let me just copy and paste it. So I'll copy, given that I have copied, so let me paste the line here, and here instead of D it is, the name of my dictionary is result. So I have taken a dictionary, and based on the values I want the sorting to occur, that is based on the points accumulated I want the sorting to occur. So just a quick recap and then we'll proceed with running. So we had seen up till distribution of points, the output even is displayed here. But before proceeding further, I'll clear the screen and I'll run. So the output is as well displayed here. It gets converged to some specific distribution. So we had seen up till there. And once we have got the convergence state, we have to rank the nodes. This is the points for node 0, this is for node 1, node 2 and so on. So we have to rank the nodes based on it. If you just keep, this is a list, so if you just apply sort on list, the fact that this node has these points is lost. That's why we'll convert it into the dictionary. As you could see here, we are converting the list into a dictionary, preserving the fact that this node has these many points, and we are applying this built-in functionality sorted on dictionary. And this is a functionality that takes care of sorting based on a given parameter, based on the points value we want to sort it. So we are using that built-in functionality, just that to preserve the fact of this node has these many points, we are using the dictionary data structure. We are converting the list into dictionary. Also, we have done this for our method, points distribution method. And once it is done, we are going to compare it with the default networkx functionality, PageRank. That will also return a dictionary, and we are applying the same sorting mechanism, and we are displaying the sorted result. We will see how is the result that we get after our points distribution method, and what is the built-in result that is obtained. We'll see how it is same or different, or what is the thing that is the node that is ranked as number 1 here, is it the same in the built-in as well. So let us see all those things. So before running, let me clear the screen and let me run for you. Let me run now. So I have got the sum network, sum distribution. I'll continue. I keep continuing. Yes, I guess I got a convergence. See, because I was seeing these two values, I feel, yeah, there is convergence. There is convergence here. So let me press hash to stop. Okay, so I have got convergence here. Okay, so this is the value we have got based on our points distribution method. Node 7 is the least ranked node and node 6 is the highest ranked node. Node 7, node 6, yeah, the same we are getting. We are getting different values here because, as I have said, if you take a different seed value, the final value will be different. But as I have said, if you take this particular value by sum of all these values, if you find, that distribution will be same. That is, here, if you take this particular value, 12 point something by 300, if you take that particular fraction, if you take the fraction, that will be same for both the things. You can verify it. This built-in functionality is using some other methodology. Also, I hope you have seen or you will be seeing another method of random walk to get the page rank values. So it is using random walk and some other methodologies, or with some other seed values, it is the built-in functionality is doing. So the values may differ, but the ranking, if you see, node 7 is the least ranked node and node 6 is the highest ranked node. That is preserved. Not only that, the ordering is exactly preserved, as you could see. 7408. 7408. Okay. 291356. 291356. Wow, this is exactly matching. So good it is. But our method of points distribution and the built-in PageRank method exactly matches. And as I said, for whatever be the network structure, there is a convergence state. There is a convergence configuration. This is mathematical proof that you can take it as an advanced material from this lecture. You can look it up. Some amount of probability is the prerequisite for the mathematical part. You can look it up as an advanced material from this. It's not very required if you are interested, and if you are a geeky person, a math oriented person, a highly enthusiastic person with math, you can look it up. The requisites are probability theory, that's it. You can look it up and you can see to it. It will always converge. There is a rigorous mathematical proof for it. Alright guys, I hope you enjoyed this activity on PageRank using points distribution method. Thanks for watching. Have a nice day.